Um, so now I'm going to share my screen. Yes, here we go. Right. So now we're going to talk about, for a very short little lecture about Fourier transforms. And I think you have heard a few times already named something about Fourier. Fourier, what is that Fourier thing? So because it is such an important thing in image, what am I doing here? I am, where is my lecture? Here it is. Because it is such an important thing in image analysis, I thought I would try to deblur a little bit what it means. It took me a very, very long time to wrap my head around about this. So I think I want to point it out to you a little bit. Okay. So when we describe music, I think many of you have seen this type of histograms before. So music is a sound, but it comes in different frequencies. So we have a feeling for it, we hear it, but it can also be represented, and you may have seen this type of histograms on your phone, or if you have like a fancy app playing music, they will show this bar will move as the music is playing. And so the same information can be displayed either as a sound or in the sum of frequencies in here. So this is something that we're quite used to seeing. Somehow it makes sense when we see it. There are two ways to display exactly the same information. And each column here represents a frequency, and then there is the amplitude of the frequency. And when we go from one form of displaying music, let's say, to another form, and we go back and forth like this, we actually do not lose any information. There is, let's say, if this is not filtered, if this is not cut off, then we can go back exactly from all this sum of frequencies into the music. We can decode that, let's say. So there's no loss of information from going from the sound to the frequency representation and back. Now, the same thing exactly is true for images. And we don't have to go into the physics of this or something like this, but basically this is an image, and it can be completely represented as a sum of frequencies. And this is called a Fourier transform. And so this is the spatial representation. So it's an image. It's the spatial representation of this image. And here we have the Fourier transform representation. And we can go back and forth. It displays exactly the same information. And each dot in the Fourier transform represents a frequency and its amplitude. And it actually also has two more things like phase and orientation, but we don't need to go into the details of this. Just know that this stuff here is exactly the same as this. It's the same information. And once we have the Fourier transform, we can make an image again. And so, yeah, why is that useful for us? So if I remind you that we manipulate light with irises and with lenses, and this is the lenses, they will focus and defocus the light basically depending on their shape. So we go from a curved light front to a flat light front, and back again to a curved light front to the image plane, and etc. like this. And then at the end, what we're measuring is the point spread function. So in the microscope, we have spaces where we have images, like the image planes, and we have the space in between, okay? and the rest of the space without images. What happens if instead of putting the sensor at an image plane, we decide to put a sensor in between where we do not have an image? That's what we're getting. Okay, we are getting this type of Fourier transform. So actually, this is something that really happens in the microscope, and we can even image it. So we have image planes where we have an image, and then we also have Fourier planes, which are the place where in between the image planes, if we put a sensor, we're measuring the Fourier transform. And the Fourier transform are not only a way to display the information, it's also a phenomenon that happens physically in the microscope. So we have basically the sample here, we have the objective, we get the Fourier plane, at the Fourier plane we get the Fourier transform, and before reaching the image plane, the interference pattern of the light coming from the sample is the Fourier transform of the final image. So now we are going to be, so we can visualize this with, if you put the camera in this plane, we can take an image of this. And then the Fourier transform contains all the information that is in the image. So we can then revert this. So it contains all the frequencies that are emitted by the sample and captured by the objective. So then afterwards we put another lens, and that one will recreate the image at the image plane. This is the way it works. So, and this is what is recorded is this final image plane. And the Fourier transform and the image contain exactly the same information. So we have here the sample plane, we have the final image plane, and here we have the Fourier plane. Okay? So exactly in the same way that we have music, we have here low frequencies, and here we can have high frequencies in the music. We have exactly the same thing in the Fourier transform image. So we have at the center, so instead of being right and left, at the center we have the low frequencies, and on the edges everywhere we have the high frequencies. So we have in the things that end up it's not a physical thing. So the things that end up in the low frequency area are all the things that are low contrasted in the image. So for example, if we can think about this background here, this is going to be a low contrast. It means if I move from one pixel to another, there's almost no variation. Same thing in the dark area of the costumes here. So there's almost no variation. All the areas that have low contrast are going to participate to these low frequencies. And so they end up in the center. And all the edges and dots, so maybe the edges of this trombone or tuba, then and the edges here on this keyboard, all the edges and the dots are high frequencies, and they end up at the edges of the Fourier transform. Okay, so this is the way the Fourier transform encodes the image in high frequency, low frequency, low contrast, high contrast. So why do we care about sharp edges and high frequencies? So this is the way, I think I've shown you this. This is the way physicists measure all the contrast thing, because this is all about contrast now. So how we have a certain contrast in our object. So we are either just before the nucleus or at the membrane of the nucleus, just like a molecule away. This is the way it is in the sample, but in our image, it doesn't look like this. The border of the nucleus is a bit blurry. You don't really know where it starts and stops. So in the contrast, we have in the image in the sample, we have actually very sharp contrasts. But in the image, this contrast is lower. It's a little bit softer. So here is something that I found online in askamathematician.com. What is the Fourier transform? What is it used for? So here we have the low frequencies. And if to the low frequencies, so this is all the background things, we can add, so we get a soft edge when we have low frequency. But if now we can add on top of that another frequency, then the two frequencies, they add up. And what happens is that the red curve gets much closer to the blue curve, which is the ground truth, the reality. And so we have edges that are a little bit sharper. So sharper edges. If now we add even more frequencies, we are getting things that get really quite close to reality. So the higher frequencies we get, so this one is a high frequency, this is a low frequency, the higher frequencies we get, the sharper the edges in our images because of that. Exactly like this. And that is because we have this possibility to go from frequency to images. The high frequency represents the edges and the dots. So we get a sharper edge. And, it means that to really define completely these very sharp edges, we need to have an infinity of frequencies and high frequency to be able to define everything. So if the maximum frequency in the image is low, then we will get soft edges. And it will be harder to segment the image because we will not, the objects, because we will not know exactly where the edges are. So in the macroscope, what happens is that the edges of the objective cut off the high frequency because this is a Fourier space area. So we have this Fourier image, but the objective has a limited size. And so due to the numerical aperture of the objective, we're actually chopping off all the high frequencies. And these high frequencies will then not participate in the final image. And this is when we're basically cutting off everything that is on the outside. So because we have the objective edges. So this is why the numerical aperture, the bigger the numerical aperture and the more information, high frequency information participate in the image. And therefore we have sharper edges and we have a higher resolution in the image. This is why high numerical aperture objectives give a higher resolution because they include more of the high frequency of the Fourier transform. So the high frequencies are cut off by the edges of the objective and they cannot participate in the formation of the final image. Therefore, we get softer edges and dots. So the high frequencies are lost, we get lower resolution, light is lost, so we have lower brightness, right? The brightness is also related to the numerical aperture. That's the reason why, because some of the light is cut off. And the inner edge of the objective limits the image resolution and the brightness, and this is what the numerical aperture actually is. So in phase contrast objective, I remind you that we have a ring inside the objective. That's not very good because it basically cuts off even more of the Fourier transform, and therefore we lose resolution and brightness when we use fluorescence. So phase objectives are very good for transmitted light images to do phase contrast and increase the contrast in the transmitted light image. But for fluorescence, they're not very good because of that ring. So please do not use phase objective for fluorescence, except if you have a very low demand on the resolution. So why do we care so much about the Fourier transform and why we talk about this? This is because it is so useful when we want to analyze images. So when we represent an image in its frequencies, we can do more complex things that are not based on the pixel intensity and XY. We can do a lot more complex things. For example, in this image, here is the Fourier transform of this image. Right? We have the high frequencies all around, and we have the low frequencies, which are everything that is soft and hardly changes in the image, including the black background, is in the center. Now, what do we do if we cut off? So we prevent the low frequencies from participating in the final image, and then we take this image and we transform it again into an image. This is what happens. So what happens is now we have basically removed everything that is in the background, and we are left with all the high frequencies will represent the edges. So we have now managed in this image to only show all the sharp edges. Okay, so this is something that is not possible when we try to segment an image. So we can do so much more when we look at the Fourier transform, when you use the Fourier transform in image analysis. If we do the opposite, if we cut off everything that is the high frequencies and we can only keep the low frequencies, then what happens? The image is blurry because we are not preserving. We're kicking away. It's basically like having a low numerical aperture objective. So we're taking away all the high frequencies in the image, and we're removing anything that is sharp. Okay. So you can see that using Fourier transform is extremely powerful when we want to analyze an image. There is so much more that we can do. Clearly, we can do a lot of things by segmenting an image in its spatial representation, but by filtering part of the images in the Fourier transform, we can do a lot. So this is the reason why you have heard of Fourier transform, of Fourier, in this course so far, and I just wanted you to know that it's a very important tool in image analysis. Okay, so why do we care? The high frequencies are the edges and the sharp information in the image. The middle frequencies are all the big shapes, and the low frequencies are the background. So things where there's no edge, it's a bunch of slow change across the image. We can filter these one or several frequencies out of the image, and this is very commonly used in image analysis to do edge detection, to remove uneven background, to do blurring, etc., etc. So it's used a lot. There's a great app called the Fourier Filter Cam. I really like it very much, but it's a bit geeky to install it. It used to be on the Google, whatever it's called, store, but unfortunately they removed it. And then there is the resolution app, which is also very nice, where you can input which objective you're using, which wavelengths, which numerical aperture, everything. And it gives you everything that we have calculated so far with the pixel size and all that stuff and the resolution. So just you can download this one. That's on the Google app and the App Store or something like this. So I am looking now at my time to see if I'm 100% off or not. And let me see. No, I'm fine. So I would like to know if there are any questions about Fourier transforms. If anyone has used it for any image analysis, for example.
I think I tried once, but was with a transmission. No, was I forgot the name. Electron microscopy.
Ah, yes, it's used a lot because an electron microscopy image is not very contrasted, so it's extremely powerful. Then it enhances the analysis a lot to be able to use the Fourier transform instead of the spatial image.
Yes, we do that.
I think Laura has tried absolutely everything. I am absolutely amazed, Laura. You have tried what is it called? Expansion. You have tried so many.
Yeah.
Good.
Yeah.
You're daring, so good job. Good on you.
Thank you.
Anyone else has encountered Fourier in their life? Okay. It's not. I want to just have a very quick summary, let's say, of the things that I think are key in this course, just so that for each of the things I'm going to say now, I hope that you can just go into your brain and go, do I know that? Yes, no, something like this. And that is because you're easily drowned into the mass of information, but really the core things are very few. Okay, so let's have a look a little bit and let's see. So what do I think are the core things in this course? Start with the scientific question, because as you have seen, especially in the last two quizzes, this is the key actually. So defining which metrics do we need to measure to answer our scientific question. And this scientific question needs constantly to be remodeled and changed as we learn about the limitations of microscopy, limitations of the sample, etc. So the scientific question is something that will evolve as your project evolves. Okay? And then we have the rest, and the rest is the choice of microscope and resolution. So depending on your scientific question and also how you're going to analyze, you will choose the microscopy technique and, try to go as fast as possible, considering all the other constraints that you have, like resolution and everything. So which microscopy technique is the most appropriate to answer your scientific question? And I hope that now you are familiar with sort of the 3-4 main microscopy techniques that we have described in here, wide field confocal basically. And which objectives? So I think that you also know you've learned a lot about the objectives, but clearly considering all the other restraints that we have, then what we'd like is to have the biggest field of view so we can acquire big data. And then we have the sampling strategy. Again, after you have matched everything with the other constraint, we'd like to go fast. And then we have, all the other constraints of the sample and the experiment. All this has to be integrated in such a way that we choose how to image and which machine works for us and which objective and which sampling. And we know that if we undersample, we're creating artifacts and missing information as well. Then we also have the contrast. So we spoke a lot about the contrast. We need to minimize all the factors that reduce the image analysis reproducibility. Like, for example, we want to have efficient imaging and no bleed through. We also want to have no aberrations if possible, like refraction and scattering. And that would mean if we have refraction and scattering, we can clear our sample. We also need to have a stable focus with a clear idea of how we focus. And we want to go low on the noise and background. And then we have the artifacts. When we have defined all this, we anyway are likely to have some artifacts in our images, either due to a little bit of bleed through, maybe a little bit of saturation, maybe a bit of noise, maybe a bit of aliasing. And what is important in that is these artifacts should not affect the interpretation of the image in relationship with the scientific question. So these are really the key for our course, and I think that you have learned a lot from each of these, and I hope that you can integrate all this into your own experiment now. So I'm going to stop in here, and I want to know if there are any questions about my little summary of the course in 1 minute. You guys have any comments or anything? Do you feel that you have learned these points? That's my hope, that you are clear with those.
I think it will take us some more time to digest all the information.
Yes, exactly. It is, but I see from the discussions, really, I see that the discussion is really going at a very high level compared to 2 weeks ago. So this is my hope. I can see that you guys, when you're discussing in group, it's really pretty cool to listen to you.
Yes, I only have one comment. So, because at first, I didn't know that this course will also include advanced optics and because all of that was really new for me, and also trying to.
You didn't know it would include what? I didn't hear.
Yeah, more optics, like for example, doing all of those advanced optics, like doing the equations to get the resolution. And I thought that was really cool, because I can finally say when taking a picture, I'm based mathematically on different evidences that I choose that resolution that I can justify. Because before I was asked, how did you choose the resolution? I was like, it's the same that I've used for forever. And that was, I also felt uncomfortable with giving that answer, because as a scientist, you kind of want to give a better answer, not just because it has been used forever. So I think that also is really nice, because you can finally, well, at least in my opinion, I can finally give an answer to a lot of questions that I had along of these years using the microscope. I finally have a good understanding so far, and I think that a lot of the things that have been given in this course I can absolutely implement in my imaging from now on.
Cool. This is very, very nice to hear. So thank you very much, Juan. It's that's exactly what I want. Even if you do not change anything at all in the way you're imaging, because it's possible that it was already very good, then at least you can understand why you made these choices and why things are the way they are. This is exactly what I want. And if your project changes, hopefully you will be able to decide knowingly what you want to do. So thank you. Very, very nice feedback.